Verify Stokes theorem for a vector field f bar equals x square plus y square into I minus 2xy into j taken around a rectangle bounded by lines x equals minus a, x equals positive a, y equals 0 and y equals b. This is the rectangle whose boundary is considered as the closed curve C. Recall that Stokes theorem gives us the relationship between line integral and surface integral when S is an open surface bounded by a closed curve C and f bar is a vector point function along the closed curve C, which is a continuous function. Then we have the line integral over C f bar dot dr can be equated to double integral over S curve f dot n into ds, where double integral over S is the surface integral and n is the unit outward normal with respect to the surface S. Notice that here the surface S is the interior of the rectangle ABED and the boundary of the rectangle is the closed curve C, along which the vector point function f bar is taken around. We have the direction of the vector point function will be anti-clockwise direction, that is the arrow marks along the boundary of the rectangle gives us the direction along which the vector point function runs around the boundary of the rectangle. We have, since the surface considered lies in the xy plane, unit outward normal to the surface n cap will be k, because k is the unit normal along the z direction where z is perpendicular to both x and y. Therefore, unit outward normal which is perpendicular to the considered surface S, which is the interior of the rectangle, will be the unit vector k cap. We are asked to verify Stokes theorem, therefore we will have to evaluate both line integral as well as surface integral. First, let us evaluate the LHS of Stokes theorem, that is line integral. We have line integral over C f bar dot dr equals line integral over C x square plus y square into I minus 2xy into j, where f bar is taken from here, and dr equals dxi plus dyj. We have r denotes the position vector where r equals xi plus yj plus zk. Here, since our required surface lies in the xy plane, we can consider z equals 0. Therefore, dr will be equal to I dx plus j dy. When we take the dot product between these two vector quantities, we have x square plus y square gets multiplied to dx and negative 2xy gets multiplied to dy. Now we will integrate over C the integrand f bar dot dr along various sides of the rectangle. First of all, let us consider the side AB. We have AB is the side which has the equation x equals a. Since x equals a is a constant value, we have dx equals 0. Since this is a vertical line, we have the variation will be along the y direction, that is y varies from 0 to b. Therefore, in this general line integral, we will give x equals a, dx equals 0, so that this complete term vanishes and y is given the limit of variation from y varies from 0 to b. Therefore, this line integral along this vertical line AB reduces to this format, that is line integral along the side AB will be integral 0 to b negative 2ay into dy, which will give us negative ab square. When we evaluate this line integral along the line BE, we have this horizontal line has the equation y equals b, which is a constant value. Therefore, dy will be equal to 0. We will give y equals b and dy equals 0 here in this general expression. Also, we have, since it is a horizontal line, the variation will be along the x direction, that is x varies from positive a to negative a. We have these arrow marks which gives us the anti-clockwise orientation of closed curve C, which is the boundary of the rectangle, will give us lower limit of x will be positive a and upper limit of x will be negative a following this anti-clockwise direction. Thereby, we obtain the general line integral along the line BE will be reduced to the expression integral a to minus a x square plus b square into dx. After integration we obtain this expression, which is the line integral along the side BE. Now let us evaluate the line integral along the side ED. Here we have the equation is x equals minus a, which gives us dx equals 0. Since it is a vertical line, we have the variation will be along y direction. We have y varies from b to 0. In this general expression of line integral, we will give x equals minus a, dx equals 0 and y varies from b to 0. Thus we obtain the line integral along the side ED is obtained as integral a to 0 2ay into dy, which gives us negative ab square as the answer. It remains to evaluate the line integral along the side dA. Here we have the equation y equals 0, which will give us dy equals 0. And since it is a horizontal line, we have range of variation will be along the x-axis or in the x direction. We have x varies from minus a to a. We will give y equals 0, dy equals 0 and x varies from minus a to a in this general expression, which will give us the line integral along the side dA. Thus we obtain line integral as integral minus a to a x square dx, which equals 2a cube by 3. In order to find out the overall line integral along the boundary of the rectangle, we will have to add up all the RHS of equations 1, 2, 3 and 4. Thus we obtain integral over c f bar dot dr, which is the line integral along the boundary of the rectangle, is obtained as sum of RHS of equations 1, 2, 3 and 4, which will give us negative 4ab square. Since we are asked to verify Stokes theorem, now it remains to evaluate the RHS. The RHS of Stokes theorem is the surface integral double integral over s curl of bar dot n cap into ds, where s is the interior of the rectangle and curl of bar is the curl of vector point function, which can be evaluated using curl of f bar equals determinant of I j k dou by dou x dou by dou y dou by dou z. This is the component x square plus y square of the vector point function. The next component is negative 2xy, and we have along z direction there are no components for the given vector point function. Therefore, when you expand the determinant and evaluate, you get curl of f bar equals negative 4y into k cap. Notice that when you evaluated curl of a vector point function, where vector point function is defined in the xy plane, you are obtaining curl of f bar as negative 4y k cap, which is a vector perpendicular to the xy plane. Recall that since our surface lies in the xy plane, the unit outward normal will be n equals k cap. Now we will evaluate dot product of curl of f bar and unit normal, which is negative 4y k cap dot k cap, which gives us negative 4y. Thus we have the RHS of Stokes theorem, which is the surface integral will be double integral over s negative 4y into ds. Here we have ds equals dx dy or dy dx. If you wish to perform integration with respect to x first, then you have to consider a horizontal strip inside the rectangle, and we have this horizontal strip will have its left end over the line x equals minus a, and the rightmost end of the horizontal strip will be over the line x equals a. Therefore, the horizontal strip varies from x equals minus a to x equals a. Hence, we have the range of variation of x will be from negative a to a. When you allow this horizontal strip to move across the rectangular region, in order to trace the complete region, yes, we have to move the horizontal strip from y equals 0, which is the x-axis, till y equals b, so that the complete surface S is traced. Therefore, we have range of variation of y will be from 0 to b. Having found the limits of integration, when you carry out the integration, you obtain double integral over s curl f bar dot n into ds equals negative 4ab square. It verifies Stokes theorem because line integral was also obtained as negative 4ab square.